Welcome to NEXTED by Nexuspaces, your technical guide to embedded systems and IoT. Today's topic is a powerhouse, the role of embedded systems in IoT. When people hear Internet of Things, they often imagine smart fridges or connected cars. But behind every smart device is a silent worker, an embedded system. It's what makes those devices actually think, sense, and respond. From edge processing to real-time control, embedded systems are the nerve centers of the IoT universe. Let's unpack the how and why. Let's start with the anatomy of an IoT device. It's not just a sensor connected to Wi-Fi. Here's the 5-layer architecture. Sensor/actuator layer collects data or performs actions. Embedded controller layer, the microcontroller or processor running the logic. Communication layer handles protocols like Wi-Fi, BLE, or LoRa. Cloud/edge interface connects to storage, analytics, or AI systems. User interface, often an app, dashboard, or voice assistant. The brain is the embedded system, usually a microcontroller like ESP32, STM32, or NRF52. These contain GPIOs, ADC/DAC, I2C, SPI, PWM, and sometimes wireless modules, all packed into a low-power chip. In modern systems, these chips run full networking stacks, device drivers, and real-time logic, sometimes using as little as 32 or 64 kilobytes of RAM. The firmware in embedded IoT devices is what breathes life into the hardware. Firmware handles sensor reads, I/O control, communication timing, and more. But when devices perform multiple tasks, like reading a sensor every 10 seconds, while maintaining Wi-Fi and responding to interrupts, we need more than a simple loop. Enter the RTOS, real-time operating system. Popular ones like FreeRTOS, Zephyr, or MbedOS provide task scheduling, preemptive or cooperative, inter-task communication, queues, semaphores, timer management, power state transitions. With RTOS, you can run a sensor task, a communication task, and a watchdog monitor, all independently and predictably. It also enables modular, scalable code, which is critical for production. An embedded system in IoT is only useful if it can communicate. That's where IoT protocols shine. Depending on the application, you'll find Wi-Fi, high throughput, high power, good for consumer devices. BLE, great for wearables and short-range control. Zigbee/Z-Wave, mesh-based protocols for smart homes. LoRa/LoRaWAN, long-range, low data rate, perfect for agriculture, environment monitoring. NB-IoT or LTE-M, cellular-based for remote assets. On the software layer, protocols like MQTT and CoAP are common. MQTT is publish/subscribe, great for real-time messaging. CoAP is request/response, optimized for low power. Embedded developers often implement these using lightweight stacks like LWIP, UIP, or vendor SDKs. Most IoT devices live far from wall outlets, so power is everything. Embedded systems use clever strategies for energy efficiency. Sleep modes, chips like ESP32 can drop to microamp levels in deep sleep. Duty cycling, wake, sample, transmit, and sleep, in milliseconds. Low-power sensors, components with sub-milliwatt consumption. Energy harvesting, from solar, piezo, RF, or even body heat. You must analyze current draw during active, transmit, and sleep states. Tools like power profiler kits or oscilloscopes help with measurement. Smart firmware design, like batching transmissions or reducing polling, is critical to maximizing battery life. Let's ground this in real examples. 1. Smart agriculture. Soil moisture sensor STM32 MCU LoRa transceiver. Data goes to a gateway, then to cloud for visualization. Actuates water pump based on thresholds. 2. Health monitoring. Heart rate plus SpO2 sensor Nordic NRF 52840, BLE. Sends data to a mobile app using gap profiles. RTOS handles periodic sampling, notifications, and battery monitoring. 3. Industrial IoT, IIoT. Vibration sensor Raspberry Pi CM4 running Python. Uses Modbus for local communication, MQTT for remote reporting. Predictive analytics in cloud using time series AI. 4. Home automation. ESP8266/ESP32 controlling relays. Works with Home Assistant, Alexa, or Google. OTA firmware updates plus secure MQTT communication. IoT is vulnerable. Embedded systems must prioritize security, even at the chip level. Key features include TLS/SSL encryption, for securing communication, e.g., HTTPS, MQTT over TLS. Secure boot, verifies firmware signature before execution. OTA updates, lets you remotely patch firmware. Device authentication, using unique certificates or hardware IDs. Frameworks like ESPIDF and MCU Expresso offer secure APIs and OTA handling. Never hardcode credentials. Use key vaults, token-based auth, and certificate rotation for real-world deployments. We're now moving beyond connected devices to intelligent edge systems. Future trends shaping embedded systems in IoT include Edge AI, tiny ML on MCUs using TensorFlow Lite Micro or Edge Impulse. 5G and satellite IoT, high-speed, low-latency connectivity for critical systems. Zero Trust architecture, security-first design from silicon to cloud. Modular hardware, SOMs like BeagleBone, Arduino Portenta, and Raspberry Pi CM4 for rapid prototyping. AI accelerators, chips with built-in NPUs, neural processing units. The embedded engineer of tomorrow will need cross-domain knowledge, from electronics and firmware to AI and cybersecurity. Embedded systems are the heart and soul of IoT. They give life to sensors, intelligence to machines, and control to our connected world. If you're diving into IoT, start with understanding embedded design, it's your foundation. Thanks for tuning in to NEXTED. Hit like, subscribe, and drop your thoughts in the comments. Got a topic you want us to break down? Let us know. See you in the next video.